All right, we're going to review parametric equations and vectors today. So first with parametric equations, what we're going to do is make a table of values and sketch the curve, indicating you also have to indicate the direction the points are going, and then we're going to eliminate the parameter, so the third variable, which in these is either t or theta, and turn it back into a rectangular equation in terms of x and y. Okay. So we're going to start with drawing our table. So we're evaluating our functions with respect to t. So, and I can see that from my x equation, the square root of t minus 1, that I have a domain restriction, that t has to be greater than or equal to 1. So on my table, I'm going to start with 1. And then to take the square root of, well, I'm going to start with 1. I'm plugging into for t. So 1 minus 1 is 0. Square root of 0 is 0. And then for y, 1 plus 2 is... All right, so we plug in 1, and we get 1 plus 2 is 3. I'm going to go ahead and plug in 2 for t, because I know that when I substitute in 2 for t, I get 2 minus 1, and that's an easy square root to take. So 2 minus 1 is 1, square root of 1 is 1, and then I'm going to substitute in 2 for t, giving me 4. Okay. Next, the next number that's easy for me to substitute in is 5. So I'm going to do 5 minus 1 is 4, which gives me the square root of 4, which is 2. And 5 plus 2 is 7. Last number I want to plug in or substitute is 10, because 10 minus 1 is 9, and the square root of 9 is 3. And 10 plus 2 is 12. All right, I'm going to go ahead and graph these in. I have, I'm basically graphing my xy coordinates here. I have 0, 3, 1, 2, 3, and 1, 4. That was a little off. Okay. 2, 7, 2, 4, 5, 6, 7. And then 10, 3, 12 is off the graph. So I'm going to go ahead and just sketch this in like so. It looks like half of a parabola. And for direction, I'm going to add my little arrows here saying that it's going in the positive x direction. Okay. Because x is an increasing function. All right, so now we're going to go ahead and write our parametric function as a rectangular equation, so we need to eliminate the parameter. So I'm going to start with my y is equal to t plus 2, and I'm going to isolate t. So y minus 2 is equal to t. And in my equation, x is equal to the square root of t minus 1. I need to substitute in my y minus 2. So I get x is equal to the square root of y minus 2 minus 1, giving me x is equal to the square root of y minus 3. And then to get y, I want to write this equation in terms of x because it makes sense in my mind. So I'm going to go ahead and square both sides, leaving me with x squared is equal to y minus 3. So y is equal to x squared plus 3. Okay, so this is my rectangular equation with my parameter eliminated. All right, let's do another one. We're going to build our table. I have t, x, and y. Go ahead and substitute in your values. Oh, actually, this time, I have a mistake. My values are that my domain is restricted from -2 is less than or equal to t, which is less than or equal to 3. So I can only substitute in times between -2 and -3. So I'll just do the whole numbers between -2 and 3. So I'm going to substitute in -2. -2 squared minus 3 is 1. And then I'm going to substitute in -1. So -1 squared minus 3 is -2. Substitute in 0, I get -3. Then -2, positive 1, and 6. For the y's, I'm going to go ahead and substitute in negative 2, giving me negative 4, negative 2, 0, 2, 4, and 6. Go ahead and graph this. So I have negative 1 and negative 4. 1, 2, negative 2, negative 2, negative 3, and 0. Then I've done this one, this one, this one. Negative 2, positive 2, 1, 4, and 6, 6. Okay, so I can see that my initial point was this 1, negative 4, which is right here, and we're swooping upward. So we're going first in the negative x direction, then we switch into the positive x direction. All right, so we're going to eliminate the parameter, giving us, I'm going to start with my y equation, though you can start with your x. We need to isolate t, so t is equal to y over 2. Then we're going to take our x equation and sub in my y value, or sorry, my t value. So I get x is equal to y over 2 squared minus 3. I'm going to isolate y. So add 3 to both sides, giving me x plus 3 is equal to y over 2 squared. Then take the square root. So I have y over 2 is equal to the square root of x plus 3. And then multiply both sides by 2 to give me 2 root x plus 3. And one thing that I have to make sure to do is change my my domain. So I know that the possible x's that I'm allowed to plug in are the leftmost x is negative 3, and my rightmost x is 6. Actually, there's no arrow here because it ends right at this point. Okay. So the rightmost value is 6. So my domain has been, we need to rewrite our domain in terms of x. Okay. All right, the last one is x is equal to 3 plus 2 cosine t, and the y's growth is going to be written as y is equal to negative 1 plus 3 sine of t. So we start with our table. I mean, you don't have to start with your table, but I am. That's fine. Okay, so I am, since we're talking about a trig functions here with our inputs as just like my angle input is not horizontally stretched or shifted. So I'm just going to substitute in our normal quadrant angles of 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then I'm going to go ahead and substitute that in. So I have 3 plus 2 cosine of 0. Cosine of 0 is 1, so 3 plus 2 is 5. And then I'm going to do pi over 2. So 3 plus 2 times cosine pi over 2. Cosine of pi over 2 is 0, so this would just be 3. Cosine of pi is negative 1, so 3 minus 2 is 1. And then we're going to repeat ourselves because cosine 3 pi over 2 is 0. So we end up with 3, then 5. We're going to repeat the same thing for negative 1 plus 3 sine t. So sine of 0 is 0. So we get negative 1 plus 0 is negative 1. Then sine of pi over 2 is 1, a positive 1. Okay. And we get negative 1 plus 3, which is 2. And then sine of pi is again 0, so we're back at negative 1. And then sine of 3 pi over 2 is negative 1, so I end up with negative 4. And we get a spin back to negative 1. Okay, so this looks like, let's go ahead and graph in our xy coordinates. Okay, -5 or +5, 1, 2, 3, 4, 5, -1, and then 3, comma 2. And I'm going to make this initial point blue so that I know where I started from. And then 1, -1, 3, -4, and back to 5, -1. So we are, this is an ellipse, and we are moving in the counterclockwise direction because our cosine values and our sine values, or well, it's because our cosine value is positive, okay? The greater, the input to our cosine function is positive, so it's moving in the counterclockwise direction like normal, okay? Let's eliminate the parameter. I have x is equal to 3 plus cosine, 2 cosine t, sorry, yeah. And y is equal to -1 plus 3 sine t. And this time, instead of isolating t and substituting in, we're going to use our Pythagorean identity of cosine squared t plus sine squared t is equal to 1. Okay, so I need to isolate cosine t, so I'm going to subtract 3 from both sides, leaving me with x minus 3 equals 2 times the cosine of t. So the cosine of t is equal to x minus 3 over 2. Same thing for y. We're going to add 1 to both sides. Give me y plus 1 is equal to 3 times the sine of t. Then I get the sine of t is equal to y plus 1 divided by 3. Now we can substitute these into our equation, giving me x minus 3 squared over 2. And this whole thing is squared, so I'll use a bracket, plus y plus 1 over 3 squared is equal to 1. Simplify this, make it look nicer. So x minus 3 squared over 4 plus y plus 1 squared over 9 is equal to 1. And again, look, this is an ellipse. Our center is at 3, -1, right? 3, -1. And I have a horizontal stretch of 2, 1, 2, and a vertical stretch of 3, 1, 2, 3. My counting was a little off. 1, 2, 3. Try that again. 1, 2, 3. Okay, that is it for parametric equations, and we'll take another look at another video for vectors.